back and look. I think they are on the optimistic side. I'll be happy, very happy to be proved wrong. If this number of neutron star events is greater than 10, I will be surprised, but pleasantly surprised. I think it's likely to be done. You know how hard it is to reach the sensitivity that you want. This is not easy, and I just can't see this jumping from 2 to 10 to 20 in the next run, but I'm happy to be proven wrong. Now, of course, that's the number of neutron star events. The number you might expect to get in electromagnetic counterparts will be less, because some of them will be in daytime, maybe 30% in daytime. I'm rounding here to integer numbers. So you might expect to lose 30% of these because they're daytime, and then we're reliant only on the radio, which would be difficult to, I think, and they may not be radio bright depending on their inclination angle. So given we're going to lose some to daytime, I think we're down at order less than 5 at most, maybe a little bit less in terms of the number of neutron stars we have and electromagnetic counterparts. Another way of looking at this is just the rates, the estimated volumetric rates of binary neutron stars. Down at the bottom are the LIGO, Virgo rates from 01, 02, 03A, and 03B. 03B is the large error bar. 03A is the solid rectangle with this range and a midpoint roughly of 300 per gigaparsec cubed per year. And so that 300 is actually not inconsistent with other constraints from short GRBs, population synthesis, which is a theoretical estimate of the number of neutron stars that come from the star formation rate and the supernova rate in the local universe, and galactic double neutron stars. So 300 is not inconsistent with all of these constraints. I expect it to be in that regime. If that is true, it's also, so the in green, here are limits, which I'll come back to. I think these are starting to become quite interesting, particularly Atlas and ZTF, very powerful wide field surveys, searching for kilonova. Have not found one independently because 170817, it's as bright as many of the nearby supernovae. It's not at peak. That's pretty easy to detect, 100, 150 megaparsecs. We have not found one, and we are looking very hard for untriggered kilonova. So the limits now are from ZTF and the Atlas survey, which I'll describe, because they're all hemisphere surveys, at about 1,000 or so. So I think it's unlikely that there are EM bright binary neutron star mergers out there, which with a rate greater than 1,000, which is now becoming interesting because it's close to the upper limit for LIGO, and actually more than the highest error bar from 03. And this will improve, these will improve and are improving daily, of course. So if around 300 is true, which is consistent with what the previous slide I showed, at 100 megaparsecs, you get about 1 per year, 1 binary neutron star event per year. And 170817 is a once in a decade event, that's the rate. 175 megaparsecs, most likely for 04, if that's the LIGO range, somewhere between 4 and 7. It's not until we get to 05, you're into the regime of 30 or so, tens of detections per year. And I think that's where the revolution will come. So 03, sorry. The 2 events, I think, which were followed up in detail. The other binary neutron star merger event, the only other one that you detected, 1904-25, very significant detection, 150 megaparsecs, combined mass of 3 solar masses on the high side, of course. So ZTF, and we covered this as well with the telescopes in Hawaii, covered the eastern part of the sky map, although of course half of the sky map was in daytime. No counterpart discovered, and we were sensitive even at 150 megaparsecs. Most of the observations, CTF, pan-stars in particular, were sensitive to objects like 17 GFO, but we didn't survey half the sky. So we're not, I think the community would feel we're not put off by large sky maps, as long as we can cover the probability. So there are many facilities, and I'll highlight a few others which are coming online, which can cover 1,000 square degrees or so, a few thousand square degrees reasonably comfortably. So it's mostly, I think it's mostly the sensitivity and the intrinsic luminosity of the events which will limit the detections rather than the area of the sky maps, as long as the sky maps are reasonably accurate over the first few days, which is really our major concern, which I'll come back to. So no detection. The other interesting one was, well, there were two other neutron star black hole mergers. This one was particularly interesting given that it was extremely well localized, 19 square degrees. This area of sky was covered by many telescopes during 03. The distance was quite large, 240 megaparsecs or so, 200 to 280 megaparsecs, the estimated distance to this object. 23 solar mass black hole and an object around 2.5 to 2.7. So with potentially a very massive neutron star, or as you know, also possibly a light black hole. The area, both of the two little blobs, were covered in detail by many telescopes. Here's a summary of just what we did in the Engrave collaboration, which controls really most of the facilities at the European Southern Observatory. We covered both of these sky regions to a certain extent. We did both. We covered all of other projects did this as well, where they covered the whole sky area, plus then also picked out the most luminous galaxies which were known to be within the distance limit and observed those with larger aperture facilities, not very wide field, but just pick the galaxies out and observe those directly, which was how GW17 or 817, the transient was found. 75 optical transients, pretty much all ruled out. 10 sources that were faint sources, lacked information that we could completely rule them out, but they're unlikely, probably background supernovae, not inconsistent with being background transients. And so no detection of any optical transient found. These are the limits. The lines in this graph, so this is time versus magnitude, but the lines in this graph, the solid lines are 0817, the luminosity for the kilonova, and the limits are from, on the left, from the wide field survey covering the whole area, and on the right from the galaxy surveys. So to summarize, about 50%, 40% of the sky area was covered to the depth of 0817, and about 90% to about a magnitude fainter, factor 2.5 fainter. So reasonably sensitive. But a little bit far to rule out an optical counterpart existing if the companion was a neutron star. So here are the lessons. Those are really the two major objects. So there were two other neutron star black holes followed by ZTF, no detection. I think those are the two most interesting ones in 03. So what lessons learned from 03? Preliminary alerts coming out in a few minutes is great. Classification and an initial alert of retraction within an hour, also great. I would say our major concern would be any changes to the map, get those out as quickly as possible. Changes to the mass is sort of secondary, because if we're pointing in the wrong place, we're wasting our time. If we're pointing in the right place and it happens to be more massive than you originally thought, that's okay. At least we're looking at something astrophysical, and we're looking in the right place, and we're taking a chance. But if we're, if the maps are out, we are effectively we are wasting our, our valuable telescope time. So I think the maps and if you've any information on the astrophysical reality, of course, those are the key things to prioritize. We'll take whatever masses you can give us, or information on the masses and the parameters of the source. But the key thing, I think, is any updates to the maps and the positions, get those out, and we will adjust our schedules on time scales of minutes to hours as we see those maps. So that sort of is the lesson from 03. I think we we were generally pretty happy with the information that we got. And it's, if anything changes, then send an alert and an updated map as quickly as possible. So the current EM searches and the outlook for 04. Here's a summary of the optical. Well, I'll give you my take on searches for kilinovae. So searches for binary neutron stars in the optical and near infrared without a gravitational wave trigger. So we've got this system called the Transient Name Server. It's run by the International Astronomical Union, or the Supernova Working Group. I'm part of that. It's based in Wiseman in Israel. Well, the database is based there. The system is run by the guys at Wiseman, but on behalf of the community under the auspices of the IAU. So anyone who discovers an optical transient can register it there and get a name. AT 2022A is the first one in the year, and it's base 26 counting for historical reasons. Since 2016, when the database has been running, there are a total of now 95,000 optical transients, pretty much all extragalactic. So people don't register stellar galactic sources on this website. This is really focused on extragalactic. The database is focused on extragalactic transients. There's nearly 100,000 transients outside the Milky Way, extragalactic transients. Are there any kilinovae in this 100,000? So the problem is that you still remember when I said they're not the kilonova associated with 170817, actually quite luminous, comfortably detectable by the main surveys that have contributed to this 100,000, this sample of 100,000 transients. So can we find any which are potentially killing? Here's a table. So you've got you're talking the same similar language. You have your binary neutron star ranges, the distances to which you will detect sources, angle averaged. So here's a rough. So this is approximate. And there's a fuzzy boundary between all of these because with an optical telescope, we can change the exposure time. We can go deeper. We may have, it depends on the sky conditions and things. But the first order, a 50 centimeter wide field telescope will get to 100 megaparsecs for detecting something like 17 GFO. The Rubin Observatory, 6.5 meter aperture, we get to about 600 megaparsecs in a 30 seconds. That's a typical survey exposure time. And so the other apertures are in here, roughly. Don't take these two, these are guidelines. So a half meter telescope can certainly get to 20.5 by increasing its exposure time, going down the sky area. But these are indicative ranges for apertures, telescopes with apertures 0.5 to 6 meters. These represent most of the survey telescopes which are working at the moment. So there's a range which go into these range of sensitivities that go into these 100,000 transients here. The problem with detecting the kilinovae, if they're similar to that of 170817, is not the peak brightness in the 42. We're reasonably comfortable out to 100, 150 megaparsecs in many of these surveys, but it's the fact that it declines by a factor of 110 days. So that's the difficulty in finding these, is that they fade so quickly. And then if you don't have follow-up information on all of these, then you lose them in the background fog of type 1a supernovae. And depending, so you need, because they fade quickly, you need a survey that is very rapid, so you can find the objects which are fading quickly. Quite possible that there are some kilinovae in there, but in the past, if someone found an object at a galaxy 200 megaparsecs, faded away the next night, hardly anyone is going to get the VLT on that and point all of the infrared instruments for the next 2 nights to find if that is an infrared bright object.
What do you mean exactly?
Well, it's days. That's days. Yes, that is days. So factor of 110 days is approximately the decline rate. So the difficulty in finding these, if they're like that, which means you need a very high, the time sampling needs to be of order a day or a few days. So I'll just give you an example. It's a project that I work on. We've got we have been for the last few years working with this facility, 2 50 centimeter telescopes in Hawaii, but each of them have got nearly 30 square degree cameras. So up until now, you can see the green, every dot is an extragalactic transit. You can see the limit down at -50. So we go down to -50 from Hawaii. And up until this year, we had been surveying the sky every 2 nights, minus weather. So it works out probably every 3 nights or so, given the given weather constraints on Hawaii. You can see the galactic plane. There's a gap in the galactic plane, just high extinction. So you can miss objects towards the galactic plane. So up until this year, we've been working, surveying the sky, similar to ZTF, mostly in the northern hemisphere, but down to -50, getting to 19.5, so sort of 100 megaparsec, the distance of about 100 megaparsecs for our neutron star, binary neutron star range. 4 times 30 seconds every night. So we do four exposures every night, 30 seconds each within 1 hour. And that allows you to track the asteroids. This is funded by NASA to find asteroids, not funded for kilanovae or supernovae, but it's a fantastic survey instrument because we can get around the whole, we can basically just do the whole sky as quickly as possible. 2 more units have been installed, Chile and South Africa this year. So now we are the first survey really to get to this sensitivity. Now we can do the whole sky every night, or between -50 and +50. And at the poles, we do it every 2 nights. But pretty much the whole sky. And we release the data publicly. But even with it, even doing the whole sky every 2 nights has resulted in an efficiency. If we look at the efficiency of recovering objects like 17 GFO, out to 100 megaparsecs, we're down to 10% efficiency recovering them. That's the difficulty, because they can pop up and disappear even with a 2-night cadence. So we hope this. So this is efficiency. This is our recovery efficiency versus distance. 10 megaparsecs, we're up about 55% or so. The flat line, of course, is the sun. So there's 40% of the sky we don't observe or so. So if we inject, so we put down 100,000 objects in our mock survey, and we see what we would have recovered given the sensitivity of every image we've taken. And we put these down randomly in the sky. Of course, 40% fall into solar conjunction, and we don't see them. And then the black line shows us the reason why. I suppose that's because insufficient detections. We require 3 5 sigma detections out of the 4. And that's how we do our samples. So we process the data every night. We can't fall behind because the telescope observes the night after. Similar to ZTF, you've got to keep up with the data processing. So the problem is that once you get to 60 to 100 megaparsecs, which is where all the volume is in the local region, the efficiency of recovery is down to 10 to 20%. So that's really the reason why I think we haven't detected anything independently to the GW without a gravitational wave trigger. At least even if you give us 1,000 square degrees, it's a lot easier than 40,000 square degrees to find. And then there is a reason to focus our attention on it, and it gives us a time limit as well. So it's just hard over the whole sky because they're faint, and it's not really because they're faint, because they fade rapidly is the reason. And ZTF are doing the same, looking for fast declining transients. So that's the reason. That's the simulation of injecting objects like 17 GFO into our data, seeing how many we recover. That's given us the limits here of 900 and we're around 1,200. So we think our efficiency will go up significantly given we've moved from 2 days to a 1-day cadence. So within a couple of years, I think we might hope to push this down towards the interesting limit that rates that you will get from the neutron star mergers. So new developments so that's ongoing. All of those searches across the whole sky in the optical are ongoing. The new developments as well for 04, there are a number of new developments. Well, our Atlas survey will be working all sky every night. Not sure what we're going to do. We might just leave it because we're pretty much surveying the whole sky every night. So we get weather permitting, we will be covering every sky map you release by default. So we have a decision to make with a science team meeting next week on what we do and how we prioritize for 04. I'm going to highlight Black Gem, which is an interesting development in the southern hemisphere. The VISTA telescope, which was one of the telescopes discovered 1708-17 in the near infrared, is not formally offered because they're changing the instrument on the telescope. but it's possible that DDT, so Director's Discretionary Time proposals, will be made available, so we may well be able to access that. If not, then we're missing a wide field infrared capability in the south, so that may, the availability of that may be reduced. In the Northern Hemisphere, there's another Pan-STARRS telescope, which is now pretty much fully commissioned, another 1.8 meter, 7 square degree field of view camera. There's an interesting development, Caltech, a 1 meter infrared optimized telescope with 1 square degree in California, led by the Caltech group, Mansley Castley-Wall and her team. And there's another development in the Canary Islands. It's a 0.4 meter, a suite of 0.4 meter telescopes, 40-10 meter telescopes. Combined, it's got 100 square degrees, and it's dedicated for gravitational wave observations. It doesn't have any other distractions. It's meant that that's what it was built for. Sort of a similar sensitivity to the Atlas, but it is dedicated and it can decide to, with Atlas, we do have to survey the whole sky to some extent because that's our NASA mission. But this one can decide on their strategy. I think just highlight the Black Gem facility, the lead institute there. I'm not involved in this, but this is led by the Radboud University in Nijmegen in the Netherlands. 3 65-centimeter telescopes, interesting design. They put them on these pedestals to take advantage of the very good natural seeing at the sea. So although they're only 65 centimeters, they easily get the equivalent sensitivity of ZTF, maybe better actually. And also this is dedicated to GW follow-up. So although it's only 8 square degrees, it's a fully dedicated facility. So there are a number of facilities coming, new facilities in 04 that are totally dedicated to gravitational wave follow-up with no other distractions, and will do large sky maps and will spend basically invest all of their time, whatever it comes out of 04. So I think in 04 there are these new developments, dedicated facilities. Everyone has sort of got their have got their proposals in, and virtually all significant aperture telescopes have some time dedicated to gravitational wave targeted opportunity programs. Certainly those that allow TOO, target opportunity programs, for follow-up. Virtually all of them have got some program approved. So virtually every optical, radio, near-infrared telescope on Earth is waiting for the start of 03, and there's someone who has time to follow up objects. But of course, we got to find them first. Most of the telescopes are narrow field, so they will require a detection from the wide field surveys before they kick into action. But most of them have some time ready to go if and when there are counterparts discovered in the optical at the arc second. You need arc second precision, of course, to find them, to locate to the narrow field telescopes. But there's a huge amount of time already available because you have to plan 6 months to a year in advance for their proposal deadlines and things. So everyone pretty much has their time approved by now. Over the next few months, there'll be some more time given out with the various packs, but much of it is in place already. So I would say the community is ready to go at any stage. Given that the rates are there, might be communities very enthusiastic with this, but we're probably looking at somewhere around 5 objects, maybe somewhere between 5 and 10, I think. Probably not in the tens of objects, unless you're telling, unless I've got something wrong here, or you're telling me something different. But it's probably going to be small numbers in 04 for follow-up, which we're happy to live with and chase those with the facilities available. But I'll highlight the outlook for 05 now, and what I think is probably the most exciting developments in this field. 04 will be great, but not as good as 05. And the major one is the Rubin Observatory, which will carry out what's called the Legacy Survey of Space and Time. You may have heard of LSST in the past, which used to stand for the Large Synoptic Survey Telescope. So the observatory is now called the Rubin Observatory, but the survey is still LSST. So the LSST name and branding still exists, but the observatory itself is called the Rubin Observatory. It's in Chile. I'll describe it. It's a 8-meter telescope. Effective aperture, though, is 6.5 meters. Projected start of science operations, as I mentioned at the start, mid-2024. There's a picture of the dome. I think that's from early this year. So the dome construction is built. The telescope is in there. This is a picture from 2019. It was built in Spain. Fantastic, very rapidly moving telescope. So the two things about, I think the three major things about Rubin are its field of view, the dedicated survey operations, and fast-moving telescope, combined with the very fast readout of the large camera, which reduces the overheads. So overheads are a significant part of survey planning, because typically if you have a 30-second exposure, often the time until you open the shutter again is often 15 to 20 seconds. So you're starting to get into the point where you're nearly 50% of half your time is spent in overheads. So if you can reduce those, you reduce the overheads, then it just increases the scientific output on the cost per exposure of the facility. So LSST has been designed to be a very short, to reduce those overheads down to, I think, about 10 to 12 seconds between shutter close and shutter open for the next exposure, which means a fast moving telescope and a fast readout of the chips. So it's the video was very impressive of this. The telescope itself, so you'll see it billed as an 8.4 meter telescope, which the full diameter of the primary mirror is 8.4, but it has this inset in the tertiary mirror. So effectively, it's effectively a 6.5 meter aperture. So the light path there's primary, secondary, tertiary, and then it goes up into the cameras, the 3-lens system, and then the camera. So this is the effective aperture, and that's equivalent to a 6.5 meter. Although the whole thing is 8 meters, it's the effective area is 6.5. Still very powerful. And here's the camera, which has been built at SLAC, 3.2 gigapixels. And that I think is still at SLAC at the minute and should go to Chile later this year. That's an image from the focal plane. The detectors look fantastic. So I've worked quite a bit in the past with the Pan-STARRS telescopes. Those chips are cosmetically challenged, I would say. It makes data processing quite a challenge. These just look beautiful. Every one of them. Of the chips, so the cosmetic quality looks great. I think they're close to specification for readout noise and quantum efficiency. So this is likely, I think the latest is it's likely to ship to Chile towards the towards the end of the year. So 198 CCDs in the focal plane. LSST will look from 300 nanometers out to 1 micron, 6 filters. Each visit will get to these depths, which maybe don't mean so much to you, but comfortably getting to a distance range for binary neutron stars. If they were the same as 170817, 600 megaparsecs per frame that it takes. So easily the most sensitive instrument for this type of follow-up. And so for survey astronomy, it's a challenge then if you want to do, so a lot of the facilities I've mentioned often just use a wideband filter when they're doing when they're surveying for electromagnetic counterparts, because you also want to find the thing first of all, and then ship off all of the higher spectral resolution, multicolor photometry to other narrower field instruments. So you want depth and sensitivity. LSST, its normal survey mode will cover the whole sky across all of these bands. What you would want too, is that we would be able to interrupt the LSST schedule and point at the sky maps in 05. So we still got work to do to convince the project that that's a worthwhile thing to do. And depending what comes out of 04, that might be an easier sell or a harder sell, depending what we find in 04. But that's still not settled yet. The door is open. And there's a group of us within the Rubin project, within the science collaborations that are forcing the issue. We've written a paper by Igor Andrioni from Caltech, large number of authors from the EM community, and some GW people as well on that, who were advocating for how you would use it. And actually, we don't really need that much time. It's a few percent when your detectors are running. We don't need it. We don't need that override time when you're not running the detectors. So I think it's a good case. remains to be seen whether or not we can get it, which I'll come back to. But even with a 10-degree field of view, the fact that LSST wants to do all of these filters, then there is what we call a cadence problem. You can't do the whole. You can do the whole sky with 10 square degrees and their overheads. You can't do the whole southern visible sky every night, but you need just one visit, so you could do the whole sky every night with LSST. That's its capability, but you need at least 2 visits because you want to both identify the asteroids for the asteroid people, and we want to rule them out because there are noise, right? So faint asteroids coincident with your galaxy are incredibly common. So after you get rid of the defects, asteroids are the most common thing in the images that we produce, the difference images we produce. So you need 2 visits, which means you need two nights to get around the sky. But if you've got 6 filters, then and you want to get around the sky in all of those, then you're down to 12 days. So then it becomes a problem of a strategy issue. Where's the moon? Which filters do you use when the moon's up? You don't observe in the U band when the moon's up. You don't observe in that bit of sky. Is it worthwhile doing for Y band, for example, Y and Z band? Do we want to do those as frequently as we want to do the others? LSST has a science requirement, a very strong science requirement. 18,000 square degrees, effectively the whole southern sky. Each point observed 800 times over 10 years. That's its science requirement. But how those 800 exposures are sliced and arranged is then still up for debate. But there is an issue, a very serious strategy issue about how it will perform. And there's tensions in many different ways because it's got to keep people happy from asteroids right through to high redshift quasars. There's a committee which is set up to come up with and they have been working. They've got at least one report which is being produced, and they are tasked with coming up with a proposal by the end of the year. It doesn't have to be fixed for 10 years. At least fix it for the first 1 or 2 years and see how that goes. That's what they're tasked with. And of course, we don't need it until 05 starts, so they can do what I hope they would do is get around the southern sky, which is the main thing. So what that we want. So the reference sky is absolutely essential for what we want to do when we're looking for electromagnetic counterparts. So here's an example of the Pan-STARRS sky, everything above -30. The advantage of the Pan-STARRS telescopes now, and CTF have it, we have it in Atlas, virtually all wide field survey systems do this. They will take a deep reference image of the sky so that when you come back and you observe, you take a difference image. So here's 17, for example. We got the reference image in the middle, the image taken on the first night on the left, subtract the 2 and your object pops up. You get little dipoles and defects and things. We deal with those, but without a reference image, then if you've just got the image on the left and you don't know what's new. So that having a reference image of the sky is absolutely essential. So I think what we want LSST, the legacy survey in space and time, we want that done in the first year of the whole southern sky. One pass at all the filters, well, multiple passes, but one good reference sky for the south, which means that when we come back in 05, you've got a reference frame of everywhere in the southern, reference image for everywhere in the southern sky. That's our goal to lobby immediately, so that we're not chasing our tails and wondering you have gaps in the sky where we can't follow up. So this is critical, which most surveys, Pan-STARRS, decals use ZTF, have built up surveys. So this is when Rubin will start, we hope. Survey operations 2024, quite a bit of commissioning. We hope towards the end of 2023, there may be some overlap with commissioning. They may decide to do some. We may be able to get some reference areas of the sky done. They may even point at some of the 04 sky maps during commissioning. Sort of interesting for them if they can get a flagship detection during commissioning. That would be something that would keep the agencies happy, I'm sure. So here's the thing, here's the interesting period for us where we want to make sure that they get the reference sky done, and that by 2026, they are ready to target sky maps in target of opportunity. And the reason we need LSST, so you might say, well, what about we have plenty of cheap well, not cheap, but inexpensive by comparison. Wide field surveys, dedicated, they're built for this. Obviously, the problem in going, yeah. The problem with going to 300 megaparsecs, that's the angle average distance, is that, of course, then the kilonova will be fainter. And so typically they will be down at 300 megaparsecs. They'll be out of the range of the 1 to 2 meter telescopes, roughly. And this is probably, I think we all think that the kilonova associated with 170817 is probably on the bright end of all of the models that are produced that predict how bright kilonova are. The one associated with 170817 is typically on the bright end of all of those luminosity functions. So there's a reasonable chance, and there's good physical arguments why this may be optimistic. And so here's the reason. So this is a little bit complicated, but let's say we pick out the one in the middle. So this is time versus magnitude. And the one in the middle just is the I band. So that's 30 megaparsecs. So this is pretty much 17 with 17 and more here, 40 megaparsecs. At 100 megaparsecs, 200 and 300. So you can see at 300 megaparsecs, I've labeled the first two columns ETF. For example, one 1.5 meter telescope comfortably gets to 150 megaparsecs. Once you get to 300 megaparsecs, then even the optimistic luminous type of kilonova is out of the range, and you're down into the 4 meter to 2.5 to 4 meter class telescope. Still possible, even at with current facilities, Pan-STARRS, DECAM. But if these are, so here's an alternative light curve of a kilonova, which is got lots of heavy elements, high opacity, quite plausible that kilonova don't have a blue component, which the 170817 did. And then we're down at 300 megaparsecs. This is down at 25th, 24th, 25th magnitude, which is really into the regime where only LSST, Rubin and LSST will get to. So I think this is the excitement. When we get to maybe 30 tens of objects in 05, they're going to be at distances that probably will require Rubin to exploit these numbers. So if we didn't have Rubin, yes, you would get many in the tens, but they may be out of the range of all of the other the smaller aperture facilities. So for me, the excitement is those high numbers, but having a facility that almost guarantees you can get, as long as your sky maps are not 10,000 square, 5,000 square degrees, if they're in the regime of a few tens to 100, then Rubin can comfortably cover those. In 05, so it's not just in 05, we highlight a few other developments which make 05 very exciting. Over the next few years, there are two galaxy survey projects, foremost in the south at ESO, DESI survey in the north. We'll be covering, here's an example here of the foremost telescope. So the VISTA telescope, which is great for near infrared, wide field imaging for kilonova. The camera comes off, this multi-object spectrograph goes on, 2,000 galaxies in one shot. These will do somewhere between 20 and 50 million redshifts. So they won't follow kilonovae specifically, but they produce a redshift catalog, which will allow cross-matching of sources with galaxies with more redshifts to be much more efficient. And that's and that increases our efficiency of finding counterparts. Because we want to match our redshift to your distances that you get. So finding them associated with a galaxy that you have a redshift for then makes this search much more efficient. So at the minute, obviously that was easy for 170817. You see from 993 could be easier, but beyond 150 megaparsecs, then the redshift catalogs become incomplete, beyond 100 even. But this will produce large numbers of redshifts, make the search for counterparts easier. There's an interesting satellite mission, Ultrasat, wide field UV surveyor. It's an Israeli led mission combined with DESI in Germany and NASA. Will launch we hope in 2025, and that will do of order of thousands of square degrees per 24 hours, maybe even the tens of thousands. So that's particularly interesting for UV bright sources. ESO, there will be a dedicated spectrometer on the MQT by then, should be there next year, and that's just dedicated to transient follow-up. The whole telescope is dedicated to time domain. I haven't mentioned James Webb yet, fantastic opportunity near the mid-infrared, particularly for red kilonova. Euclid will be interesting, again, not the fine transients, but the data giving space-based resolution at any particular point in the sky for galaxy identification combined with these galaxy surveys. So I think 05 just opens up lots of other opportunities, as well as having the target of opportunity time with Rubin. So conclusions, as I started with, the potential of multi-messenger astronomy has been there since 2017, but hasn't really been realized yet, as we've only one discovery. Probably the rates are a little bit lower than our previous expectations after 02. For 04, my suspicion, I think all of us are thinking probably less. We're probably going to get a number of brand new neutron stars, but not large numbers. Roughly half may have counterparts detected given solar conjunction. For EM astronomy, for electromagnetic astronomers, there's tremendous interest. Large resources are invested for dedicated facilities and also on national facilities, time allocated. But we need detections before we do anything else. And I think the major change in this field, I think 04 will be sort of similar to 03, only a bit better. But the big change in this field is in 05, when you reach design sensitivity and the Rubin Observatory comes online, and then we're tens, dozens of detections per year, we hope, with counterparts. Thank you.
Questions? I've got one. Yeah, stop.
I'm curious about collaboration. I'm curious about collaboration. And maybe it's actually less relevant than I thought. How much better a search could be done if astronomers could agree in advance to choose sections of the sky or otherwise specialize in some way that's appropriate to their instrument? Or are there so many wide field instruments now that are available that all the sky is sure to be covered independent of any level of coordination?
So I think there is an initiative to do that, or at least to attempt to coordinate in an informal way. So attempt to coordinate formally and to get all of the projects to sign up to, say, a central coordinator who would say, hand out areas of sky and sensitivity targets for those to reach. I think probably won't happen in this 6 months, and there doesn't seem to be an appetite for that. I could probably tell you why, go into details why, but I don't think there is. But there's a project called Treasure Map, which wants people to submit where they're pointing and their sensitivities, about what they intend to do and what they have done. And so you can see what others are doing and then make your own decision. A reason not to coordinate it too much is that there are not many telescopes exactly at the same longitude, which will do exactly the same thing. So we saw with 1708-17, when that was observed in Chile, then it went to Hawaii, then Australia, South Africa, back to Hawaii. And so you get 4 points in 24 hours. And we saw the evolution in 24 hours, particularly in the blue bands. So there is an argument for everyone to, so if you've got let's say you've got 100 square degrees, there's an argument for everyone to do that 100 square degrees separated by longitude. So you do get temporal information. Of course, what you want to do is absolutely maximize the chances of detecting the object, first of all, because it might be too faint for everyone. And you've all wasted your time going too shallow, whereas you should have gone deeper. So I see that there's an appetite for informal coordination, but not yet the formal coordination would say, I'm going to do 10 square degrees to twice the depth, and you do the others. People want to make the discoveries themselves, and so that's really what's driving the individuality.
And while I've got the microphone, do you see a need for some more communication between the gravitational wave field and the astronomical community? That's an easy thing to do. It's something that we could really make progress on the next 6 months if we wanted to have a couple of meetings or something like that. but maybe we're already to the point where you know what kinds of alerts we're going to give. Maybe some discussion of how we specify mass ranges, and we're done, right?
Yeah. So yeah, I think what I'd noticed previously was, so there's some events which have got a probability of being terrestrial or non-astral, which is maybe of order 10% or so. But I think we were getting information from some people within LIGO Virgo going, yeah, I think that one is real, or other ones going, just forget that one. You know, there's a reason why that's 10%. So though you're giving us all of the information that you believe, it does truly represent the data and the pipelines that you provide. And there's no issue there. There probably are insights that you have that could guide us a little bit more. So I think the formal information we're getting is fine. I think any changes to the maps, as I said, is probably the most important thing. Mass estimates, if you could give us the mass ranges you could give us were good, useful, and people made decisions. I think probably the area of concern is that mass gap, where some of those could well be neutron star black holes, and people would invest the time in those, but not if they were, you know, towards the higher end, perhaps. So yeah, mass is the one significant figure is sort of always the thing I've said, and that's probably enough for people to make their decisions and how they invest the time.
Let me, yeah, I see many questions. So there is a question also from the, there is a question to have accurate follow-up. What is the importance of having mass information? So I have the same question afterwards. It is sufficient information that an NS is expected in the events. Would it be important to give out the information that is an IMBH event?
That is an IMBH?
Yes, intermittent mass.
Yeah. So some surveys will do that. So there will be, given the range of facilities we have, there will be. So for IMBH, first of all, there will be. I can't speak for all the surveys, but I know that there's definitely interest in some of them doing the sky maps of IMBHs, because who knows what you're looking for. There was a suggestion for a very high mass event that it might be happening within an AGN disk, and there was a flare in the AGN that may have hardened the binary and caused it to coalesce. So I think some surveys will do the IMBHs if you give that information out. And how important is it for masses? So it's very important for us to get an idea. So mostly they won't just follow 20 solar mass black holes, probably, because you'd be producing too many of them. You can't do them. Some surveys will be doing the whole sky anyway, so you won't have a look, but there'll be very few which will go deep and do all of the black holes. Black gem might, go to might. So just narrowing it, the more information you can give us on the masses, the better our decision-making typically will be. But as long as we have it to one significant figure, you can make that decision. If you tell us it's likely a neutron star, that's good, but just what you gave it in the matrix, what you gave us before was okay. The next level up would just be one number.
Let me associate my question. Sorry again. We said that masses are not. Of course, it's important to know it's an S and an IMBH. Giving a low latency alert faster than what we do right now, is it of any use? Probably it's for use for X-rays and gamma rays, but for the optical. Does it help more, or is it a good, if we are within the limits that you can? I would think so from what I followed. Yes. But
so yes, we wouldn't be advocating for faster but more accurate information. So if you want to take another 30 minutes to give us the right sky map, that's better doing that than getting a sky map which is slightly off in a minute. But is actually isn't the final sky map. So it's more the accuracy of the sky map is the most important thing than the latency. Others will tell you different because they want to get there very quickly. But I think on reflection, when people look at it, what you want to do is always be when you point your telescope, if that's 2 minutes afterwards or 20 minutes afterwards, you want to be pointing at the right place. So it's more accuracy than the latency was good. I think. But it's accuracy.
I had a question regarding the background reference image. I understand that you need to take a reference image with the same camera and the same spectral properties and all that. But is there any way to make use of, for example, Gaia information also for the background?
So yes, so Gaia is very useful, and other facilities as well. because it's been continually doing a survey of the sky. So anything that pops on in Gaia as a variable source, that's already that's in a Gaia database. And we can search the Gaia alerts and say, oh, that was found as a little variable object in 2016. So we rule it out. It's almost certainly a variable star repeating. So cataclysmic variables in our galaxy are fast transients that mimic kilonovae. And often they're found just by chance in coincidence along the line of sight to a host galaxy. So anything that has a history of variability in Gaia, we can rule it out immediately as being counterpart. And so Gaia's database of alerts, and also all of the others, ETF, Atlas, we can immediately cross-correlate any new detection with all of those and say, there's activity back in 2017. It's probably a CV or a variable star or an AGN. And so it's ruled them out. So it is very useful.
Sorry. There is Frederick has a question. Immediately afterwards, it's you. And yes.
Okay. Yeah, you mentioned a number of dedicated instruments or programs already put in for follow-ups.
Yes.
For 04.
Yes.
I guess if it's a dedicated instrument, it'll do that all day anyway.
Yes.
The programs you put in, how will they deal with a potential, always possible delay in 04?
Oh, how will they? Yes. So effectively, what most telescopes do, if you put in a program for target of opportunity, they overfill that a little bit. And so they have enough programs, if you don't trigger your time, they have enough other programs that will use that telescope time. So for example, at ESO, if we have time on the VLT, something like 100 hours, we don't use that 100 hours, that won't get filled by other programs that are doing other things. So effectively, we lose the time, they have to reapply. But the telescope's never idle, it's always nearly always doing something.
And then just for my own curiosity, really, you've looked mostly at kilonovae, everything you've presented is that the only transient you can imagine? Or is there some other reason why you consider only that one and neutron stars? And you've mentioned the 1905-21 event, which was the Zwicky one, but nothing else you want to look at or you'd like to look at that you could imagine? Anything exotic?
Yes, there are. I mean, I focused on this because you imagine with compound binaries, whether it's a neutron star black hole or two neutron stars, it's a small amount of mass and it's radioactively powered, which is what I call a kilonova. But so neutron star black holes are interesting. The range in their predictions for the luminosities of those range from much fainter than 17 to a magnitude or 2 magnitudes brighter. So some sort of weird transient with a neutron star black hole potentially. There are predictions if the neutron star merger, if you form a stable neutron star, it's potentially a magnetar that boosts your energy by several or by an order of magnitude. In some cases, certainly a few astronomical magnitudes, so factors of 2 to 10. That's possible. And then the other one is something exotic, either in the binary black holes, like this one, which is more speculative, but people will look at it. I focused on this because so it helps define your strategy. And then the other one, of course, is any burst events which have been released but always retracted. So I think if there's a highly significant burst event, we don't really know what we're looking for, but they will be covered almost certainly by many of these facilities, particularly if it's high significance.
There is a question by Frederic Marion. In terms of science, how do we expect going from a handful of electromagnetic counterparts, for instance, 04, to several dozens in 05 to be a game changer? What are the main questions that can be addressed with a large sample?
So I think the first one, even a few, would be the origin of the heavy elements. So for the odd process elements heavier than iron, the total ejecta mass and the composition and the rate of these events will determine whether or not they are really the main channel behind production of the R process, or there's something else. So there's a suggestion that certain type of supernovae produce much of the R process. So I think the origin of the heavy elements from the diversity of the kilonova population is a science driver. I think there are people particularly interested in the equation state of neutron stars, which is one sample of events. Each knot would probably require in the dozens of
30.
probably, yes, of
30 would be okay.
30 to 50. So I think in 05, there's a real opportunity there to go for each knot. Although some people argue even more in the hundreds. So I think those are the three things. Would be origin of the elements, equation of state of neutron stars, and H knot are the major drivers.
Other question?
The number of tests of fundamental physics.
Okay.
Just by having one more.
Yes. Yes.
So, if not, thank you again.